Hey everyone, welcome back to Rock the JVM. This is Daniel, and in this video, I'm going to show you how you can solve a problem like Sudoku in Scala with backtracking and recursion. So this is one of the more fun, easy programming videos for those of you more beginners in Scala or learning to think in Scala or functional programming or recursion. So as always, the way to make the most out of this video is to write code with me, and whenever you need to refresh your memory about the techniques or the approach of this problem, just refer back to the video or to the written form at the blog, where I'm also going to describe this in written steps. All right, so I'm back in my code editor where I have a simple object with a main method, and I'm going to show you how we can solve a Sudoku problem. Now, we will need a Sudoku example, so I'm just going to go online and search for some Sudoku solver, and Sudoku solvers are all the rage on the internet, and we even have a lead code problem, which is an example of an interview problem. So we have a Sudoku solver. I'm actually going to grab one of these inputs here. So the board is this little array. So we're going to consider a Sudoku board like this, where every cell is a character, or in my case, I'm going to consider those as integers. So I'm going to simply grab that. I'm going to say val, let's call this problem as, and I'm going to paste this little thing. And I'm going to consider the arrays here as arrays. So I'm going to start replacing some stuff. So I'm going to replace this little thing with a parentheses and a \n, and let's try to replace all. All right, so we have this little problem, and then I'm going to replace all quotes with nothing because I don't care about that, and I'm going to replace all the dots as, and this is not regex, I'm going to replace that with zeros. So I'm going to replace that. So we have a simple list, and then we are going to simply use some IntelliJ trickery to manipulate that. So I'm going to say list, not list, but I'm going to use array. And the first thing is going to be an array of array. All right, so this should be pretty much it. All right, so we are going to have our application here. I killed some of my Scala syntax, but that's no biggie. So we have an array of arrays. All right, so this array of arrays is going to be my Sudoku board. Now, what does the problem with Sudoku say? I'm pretty sure you've seen Sudoku before, you've done your own million Sudoku exercises. The Sudoku board problem specifies the fact that we need to fill in our little board, which is the little zeros that you see here on screen, with numbers 1 to 9, such that every row, every column, and every 3x3 box will contain all the numbers from 1 to 9 exactly once. Now, by a 3x3 box, I mean a mini cell, which is 3 rows and 3 columns deep. So this is a box, this is the next box, and then this is the next box as well. And this can be displayed a little bit more clearly with a visual diagram like this. So notice the thicker walled boxes, these are the boxes that count. So every row, every column, and every box will need to contain all the numbers 1 through 9 exactly once. This is a constraint satisfaction problem, and the technique that I'm going to show you here will apply to many of such constraint satisfaction problems. Now, let me go ahead and print our little Sudoku board a little bit cleanly so that we know what we're dealing with. So I'm going to write a function, let's call this print, that takes a Sudoku as an array of integers, and this just returns a string. So I'm going to, first of all, group the original array into 3 groups. So I'm going to split the original array into 3 groups like this. I'm going to have Sudoku grouped in sizes of 3, and then I'm going to map every group. So I'm going to say big group, and I'm going to return a simple string out of this big group. So I'm going to say big group dot map. And every group will have a single row in the original Sudoku. So I'm going to have a row. Then I'm going to group all the rows into 3 pieces. So I'm going to have something along the lines of this, something like that. And I'm going to split this into groups of 3 as well. So I'm going to say row grouped in chunks of 3, and then I'm going to map every small group, so small group. And I'm going to type in all these numbers in a one by one with a space in between them. So I'm going to say group.makeString, not group, but small group. So small group make string, and I'm going to separate these by spaces. So I'm going to type in a space before, a space between the numbers, and a space at the end. This is going to be a small group. So in between every two numbers, I'm going to have a space, and before and every small group, and after every small group, I'm going to have a space. Then I'm going to type in another make string, so make string on this one. So I'm going to type in a small separator here, a small bar in between these groups of three. So I'm going to say make string with a bar at the beginning, a bar in between them, and a bar at the end. And then I'm going to say make string and then make string so that we print our first array. I might add a little bit more tokens in between. So let's see how that looks like. So I'm going to say print line, print problem. And then let's see how that looks like. I think this is going to return a single string with no new lines. We can fix that very, very quickly. First of all, let's compile. All right, so we have these little bars as a single string. All right, we need to fix that. So I need to add a new line after every row. So I'm going to add a new line in between every single row. So I'm going to say make string with a \n. Let's try this out again. All right, and I will also need a \n in between every group. So I'm going to have a make string at the very end, and I'm going to type in some dashes like this with a \n, and I'm going to repeat that. So I'm going to have this little thing. Then I'm going to start with \n and type in these dashes in between two groups. And then the final one is going to be a \n at the beginning because I don't have that. So I will use something along these lines. Let's see how that looks like. All right, so it looks something along these lines. Good. So we have our little table. We can print this a little bit more nicely, but I'm going to keep it at that. All right, good. So we have our little print function so that we know our Sudoku board. Our Sudoku board looks something like this. Okay, good. So we have our print. Now, we will need a function to validate whether a value that we want to place at a certain set of coordinates, like a row and a column inside these two-dimensional matrix, will fit, or rather will satisfy all the constraints of our Sudoku game. So I'm going to define a small function called validate, and I'm going to pass a Sudoku problem as an array of int. I'm actually going to type that as a type annotation. So I'm going to have a type alias. Let's call this board as array int, and this is not going to be a val, but a type, of course. So I'm going to type it as board, not board as in having nothing to do, but board as in a Sudoku board. And I'm going to have let's call this x as an int, y as an int, and a value that I want to place at these coordinates. This is going to be an int, and the validate function is going to return a Boolean. All right. Now, what are these arguments? The x coordinate is the horizontal coordinate. The horizontal coordinate meaning the column at which I want to put in this value. So I'm attempting to place this value at the coordinates x and y, or rather row y, column x. This is what the x and y coordinates will mean. And the validate function will return true if the value satisfies the constraints of the Sudoku board, meaning that the row on which this value will sit on will have all the numbers 1 through 9 exactly once, or rather, because the board is complete, it will not have this value that I want to place more than once. All right, and same for the column and same for the 3x3 box corresponding to the coordinates x and y. All right, let's break this down. First of all, we will need the row. So I'm going to have my row as Sudoku at index y. The y coordinate is the vertical coordinate, so vertically. Now, vertically means selecting the row of this array. So a row of the array means Sudoku at index y. The column is going to be not Sudoku of x, but rather selecting from every row the xth column at every row so that we can return a single collection of items. So I'm going to have Sudoku dot map, because Sudoku being a two-dimensional array, it's actually an array of arrays. So from every array, which is a row, I will extract the xth coordinate out of that. So I'm going to have underscore dot apply at index x. So underscore means that this is the row. I'm actually going to type that as r arrow r dot apply x, which this is the same thing in Scala. And then I'm going to obtain the box. Now the box is a 3x3 little collection of items, and I will need to extract the box index at the horizontal and vertical coordinates. And because we have x and y being values from 0 to 8, these are the indices that we can use, I will need to determine which box this coordinate belongs to. So I'm going to have my box x as x divided by 3. This is the box coordinate from 0, 1, 2. And I'm going to define a val called box y. So box y as well as y divided by 3. And this is the box coordinate at index y. So if I split my little Sudoku board into 3x3 boxes like this, let me select, for example, this number 5 here. The number 5 is at the coordinate x equals 5. So 0, 1, 2, 3, 4, 5. This is the column. And the y coordinate is index 1, 0, 1. So this number 5 here, I'm actually going to add a little comment here. This little thing sits at x equals 5, y equals 1. Now, the box coordinate at index x is going to be 5 divided by 3, which is box x is equal to 1. That is, box number 0 was the one on the left here, the one that I'm highlighting with my mouse. And the box x index 1 is this second box over here. And box y is going to be 0. That is 1 divided by 3, that is 0. So box row is going to be 0, box column is going to be 1. I hope this little ASCII diagram helped in isolating these values visually. All right, so we have identified box x and box y. Now we need to find out all the values in this box, in this 3x3 box. So I'm going to have my val, let's call this box, and I'm going to run a for comprehension here. So for all the rows between box x plus 1, box x plus 2, on both row and column, I'm going to identify the value at these coordinates in the original board. So I'm going to have, let's call this yb, in the range box y times 3. This is the real index at the start of this corresponding box. So for this box at index 0, 1, I'm going to start the rows 0, 1, 2. So I'm going to iterate from box y times 3 until box y times 3 plus 3. So these are going to be all the indices for rows in this box. And same for x. So I'm going to have x be in box x times 3 until box x times 3 plus 3. So same for columns. Then I'm going to yield, and then I'm going to select the value at these coordinates. So I'm going to have Sudoku at row yb. So this is the vertical coordinate, and the horizontal coordinate is xb. So these are the values in the box. So we have the values on the row, column, and box. At this point, the value here that I want to place at these coordinates x and y will satisfy the constraints if the current row, column, and box will not contain this particular value. So if I say row count, and I'm going to pass a lambda here, underscore must be equal to value must be equal to 0. So there is no occurrence of this value on the row. And there is no occurrence of this value on the column. So column count underscore value is 0. And box count underscore value is equal to 0. So this is the predicate that the value will need to satisfy to pass this little validation function. For example, if I want to place the value in this box, the number 4, let's say, the number 4 in this box, so I'm going to add a little space here so that I remember where I placed it. The number 4 here satisfies the predicate for row, column, if you look at the value 4, and its corresponding box. So let's print out. So print line, I'm going to say validate on this board. So I'm going to have my problem. the x-coordinate is going to be the number 5, so the index on the column, the index on the row, which is number 2, and the value is number 4. So this should print true if we wrote the function correctly. Let's see. All right, so this does not satisfy the predicate. Why is that? Well, it's because I've already filled in the value, silly me. I've already placed 4 here. What I mean here that this validate function needs to validate the value before storing it on the board. So I'm going to remove the value here. I'm going to place it as 0 again. I'm going to rerun the function, and this time it should return true. All right. Good. So I will need to validate the potential placement of this value at these coordinates before I actually do place the value in there. All right. Let's try another one. Let's see if the number 5 is allowed in this box, and it should not be allowed because the number 5 here is present on the column. Let's see. So in this case, we should return false. I'm actually going to copy this. So on the number 4, we're returning true. On the number 5, we return false, as you saw. And let's try another one, which is a little bit tougher. Let's say the number 7, because the number 7 is not present on the row or column of this coordinate, but it is present in the cell, and the cell is the trickiest to compute. All right, so we have false, false. Okay, at this point, our validation function should work pretty well. Okay, now the algorithm itself, let's do the solution. So let's write a function, let's call this solve, which takes my Sudoku board, which is a board, and then I'm going to take some coordinates, x int and y int, and this means that I'm going to solve the Sudoku board starting from the x and y coordinates. Obviously, I'm going to call this function at the beginning from indices 0 and 0 because the algorithm will try to fill all the matrix by going through all of the cells one by one. All right, so this will return unit. This will simply try all possible solutions. All right. Here's the algorithm, or rather the technique. So I'm going to assume that at x and y, these coordinates, I don't have any value, and the x and y coordinates are proper coordinates in this matrix. So I'm going to do some checks in here. So I'm going to say if y is bigger than or equal to 9, this is the max index row-wise in this array, then I'm going to return unit. This is going to be the final finalizer of the method. If the y-coordinate is bigger than 9, then the Sudoku board is complete, so I'd rather not return unit, but rather print the Sudoku board. So I'm going to say print line on print Sudoku. I don't really like the name of this function. I'm going to call this pretty string. All right. And then I'm going to say if the x-coordinate is bigger than 9, then that means at this iteration phase, I've exhausted one of the rows, so I need to move down a row starting from the beginning. So I will need to call Sudoku on, not Sudoku, I'm going to call solve on the same Sudoku board, and I'm going to start at the row, at column 0 on the next row, so y plus 1. How that works is that if at some point of the algorithm, the x-coordinate arrives at the end of a row, the next item that I want to place inside the array is going to be on the next row at index 0. This is why I've changed these parameters to 0 and y plus 1. Otherwise, if the Sudoku board already has a value inside, then that means it's part of the original problem. So I'm going to have if the Sudoku at this row, which is denoted by the vertical coordinate, and the column denoted by the horizontal coordinate is bigger than 0, which means that this value is already set in the Sudoku board, then I'm going to jump over it. So I'm going to try to solve the next cell on the right. So I'm going to say solve on the Sudoku board, and I'm going to use x plus 1. This is the next cell to the right on the same row. Good. And if it just so happens that x plus 1 is then bigger than 9, then the next recursive call will go on this condition, trying the next row instead. All right, so this is pretty much my sanity checks. This is a final solution. Then I need to check, or I need to fill in the next row. Then this one need to fill in the next cell. So this is cell to the right. And then otherwise, I will need to try out all possible solutions. So I'm going to try out all the values from 1 to 9. So I'm going to say 1 to 9. This is a collection from the elements 1 to 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm going to filter only those that are valid for this particular coordinate. So I'm going to say filter. And considering the value that I'm going to attempt to fill into the Sudoku, then I'm going to run the validate function. So I'm going to say validate on the Sudoku problem xy and that particular value. So I'm pre-validating the possibility that I might fill in this particular coordinates with this particular value. So this will give me just the set of the numbers 1 through 9 that are possible, that are valid Sudoku at this point. And then I'm going to say for each. So for every value, I'm going to, first of all, fill the Sudoku board with the value, then try the next cell, and then remove the value. So filling in the Sudoku board with the value says Sudoku at index y and x, this is the row and column, needs to become the value that I'm just considering because I've already validated, so I'm going to fill it in here. Try the next cell. That means calling the solve function recursively. So I'm going to say solve on Sudoku, and I'm going to try the next cell, x plus 1 and y. And then I'm going to remove the value after the recursive call has finished exploring all possible solutions. So I'm going to say Sudoku at y and x is going to be 0. All right, so at this point, I think we're done. The recursion will take care to backtrack because after the recursive call, we are backtracking, that is, removing the value that we've just set and leaving space for the next value to be tried at the later stage. All right, let's try to see whether this Sudoku has a solution. So I'm going to say solve problem. And I need to pass in some arguments. X, I'm going to give this default arguments of 0 and 0 so that I don't have to pass them myself. So solve problem should give us all possible solutions for this particular board. I think because I've copied this from lead code, I should only get a single solution. All right, so we have true, false, false, and this is the solution that we obtained. 5, 3, 4, 6, 7, 8, 9, 1, 2. So we have 5, 3, 4, 6, 7, 8, 9, 1, 2, and let's say a random column like 8, 5, 2, 1, 3, 4, 7, 9, 6, 8, 5, 2, 1, 3, 4, 7, 9, 6. This is the solution that we were waiting for. Now, a few discussions here. This is, first of all, brute force, so I'm not doing any sort of smart filtering on solutions by looking at other cells in the rest of the on the rest of the lines or the rest of the boxes. There are techniques to solve Sudoku a little bit faster, but this is just brute force. That's one. The second thing is stack recursion, because here I'm doing tail recursive on just a bunch of branches, but on the critical one on backtracking, I'm doing stack recursion in the middle of the algorithm here at line 37. But stack recursion is not really a big thing because the maximum recursion depth is the size of this matrix over here, sitting at 81 elements. So the recursion depth is never a big problem in this case. All right, folks, this was a Sudoku solver in Scala. I hope you enjoyed it. If you did, there's more where that came from. I have a 15-hour course on data structures and algorithms in Scala that will help you practice the sort of mindset that you learned in this video. So I left a link in the description if you want to check that out and prepare for interview problems like this in Scala and recursion, tail recursion for that matter, and master those data structures. In the meantime, go ahead and click the like button for me and subscribe to the Rock the JVM channel for more videos like this, and check out my website at rockthejvm.com. I have literally hundreds of hours of videos and materials on everything in the Scala ecosystem, and not only. So I left some links in the description if you want to follow me on your favorite socials. In the meantime, folks, I'm Daniel, signing off.